Hi, my name is Junze. I'm a student at Boston University. Today, I'm going to present efficient alternative minimization with applications to weighted low-rank approximation. This is a joint work with Zhao from Adobe Research, with Mingquan from the University of Illinois at Chicago, and with Lichen Zhang from MIT. This is the table of content. First, I'm going to present the background and our goal. Second, I'm going to present our main algorithm and our main theorem. Finally, I'm going to present how do we achieve these results. This is a definition of low-rank approximation. Given a matrix M, which is an n by n matrix, the low-rank approximation problem with rank K asks us to find a pair of matrices X tilde, Y tilde, which are n by K matrices, such that the Frobenius norm of M minus X tilde times Y tilde transpose is minimized over all rank K matrices X and Y, where this norm represents the Frobenius norm. This is the weighted low-rank approximation. Given a target matrix M, which is an n by n matrix, and a non-negative weight matrix W, which is also an n by n matrix, but all of the entries of the matrix W is greater than or equal to 0. The goal is to find X tilde and Y tilde, which are n by K matrices, with the Frobenius norm of W circled with M minus X tilde times Y tilde transpose is minimized, where this circle represents the Hadamard product of two matrices. Here, I give an example of the Hadamard product. The Hadamard product is a binary operation between matrices. In this example, the Hadamard matrix between two 2x2 matrices is also a 2x2 matrix. Each of the entry is a product of the entries of the previous two matrices. Here, I will explain why do people study this weighted low-rank approximation. Theoretically, the formulation of the weighted low-rank approximation covers many interesting matrix problems. For example, the classic low-rank approximation can be recovered by setting W is equal to 1n times 1n transpose, where 1n represents the vector whose dimension is n, and all of the entries are 1. And the matrix completion problem is by observing a subset of entries of M equivalent to picking W as a Boolean matrix. In practice, it is often the case that some entries of M are more important than others, and some entries can be completely ignored. So it is natural to look for a weighted low-rank approximation. For example, in natural language processing, in collaborative filtering, in ecology, and in chromatin conformation and reconstruction. Prior works focus on showing that the general weighted low-rank approximation is NP-hard, even if the ground truth matrix is rank 1. The hardness is further enhanced by showing that assuming the random exponential time hypothesis, this problem is hard to approximate beyond a constant factor. Despite this hardness, many approaches have been proposed. For example, one work implements the gradient-based algorithm, and other works use the alternating minimization framework. Also, the other work develops an algorithm based on the expectation maximization. And our goal is to study the question, is it possible to obtain a faster and more robust alternating minimization-based algorithm with a similar convergence rate? In this work, we give a positive answer to this question. Now I'm going to introduce the assumptions that we have. We have 3 assumptions in total. Assumption 1 states that the largest row norms of the left and the right singular factors of a matrix should be close to their average values. This is to avoid the scenarios where the matrix has very weak signals, making it difficult to recover. The assumption ensures that the row and the column space of M star are well distributed over its coordinates, avoiding the concentration of values in a few rows or columns. This concept is standard in matrix completion tasks. The second assumption deals with the distribution of the weights in matrix W, where W is considered a binary matrix. The assumption states that it should be it should not be too sparse. In other words, each row of W should have a sufficient number of non-zero entries. This principle is linked to ensure the adequate information of matrix completion tests. In a more generalized sense, when dealing with non-negative weights, this assumption also put a limit on the maximum magnitude of any entry in W to prevent degenerate scenario. When considering W as a binary matrix, the assumption 3 implies that selecting a subset of rows of certain matrices should still maintain certain geometric properties. Essentially, this means that any subset of rows of U and W should still form a basis that is close to being orthonormal. This can be seen as a stronger version of the incoherence assumption, focusing on the preservation of certain mathematical properties, even when considering the subset of the rows of these matrices. Now I'm going to introduce our main algorithm. It starts by setting specific iteration counts and accuracy parameter. Our algorithm enters a loop where it alternates between two steps for a predetermined number of iterations. In each iteration, it first performs a fast multiple regression using the current matrix, followed by a click operation to zero out the rows with large norms, and then a QR decomposition. The process alternates between updating matrices X and Y. The algorithm outputs a matrix M computed as the product of xt and yt minus 1 transpose. This is our main theorem analyzing the main properties of our previous algorithm. Given a noisy, possibly higher rank observation M, which is an n by n matrix, where M star is the rank K ground truth and N is the noise matrix that satisfies the assumption, there is an algorithm, namely the algorithm in the previous slides, that use the random initialization runs in O of log 1 over epsilon iterations and generates an n by n matrix M tilde, such that the spectral norm of M tilde and minus M star is less than or equal to O of epsilon to the minus 1 times K times tau times the spectral norm of W circle with N plus epsilon. The total running time is as follows. Next, I'm going to introduce how we improve from the previous work. In previous work, at each iteration, the algorithm alternates by solving two weighted multiple response regression. Starting with an initial matrix Y, it tries to find a matrix X, which is an n by K matrix that minimizes the Frobenius norm of W circle with M minus XY transpose. Then it zeroes out the rows of X with large L2 norms, and then use QR factors of X to proceed. Finally, it alternates and solves the minimum of the Frobenius norm of W circle with M minus XY transpose, given the new X. Previous work requires exact solution for the multiple regression problems in each iteration. However, we provide a robust analysis showing that the approximate solutions are feasible, as long as the solutions are close in spectral norm. Second, previous work heavily relied on the closed form of the regression solution. However, we use a decomposition of errors to accumulate the approximation solved errors into epsilon terms. Thank you for watching. This is our works cited pages.